Quantum teleportation is a very exciting and interesting problem. But up to this point, considering the modern state of quantum computing, it is not really needful. On the other hand, there are quantum algorithms that even today are quite important. I'm talking about the quantum cryptography protocols. During this week, we already learned a very important thing, that one cannot make a copy of an unknown quantum state. This result, known as no-cloning theorem, is very restricting, and it does not allow us to do many things we would like to do. For example, we would like to estimate the coefficients of the basis vectors in some unknown state. If we were allowed to make copies of this state, then we could estimate the probabilities of each measurement outcome by measuring as many copies as we need. And these probabilities would give us information about the coefficients, absolute values. But no, we can't do that. And as always, or at least this happens quite often, the restriction for one kind of problems becomes an opportunity for another kind of problems. One of the fields where restrictions and difficulties are consumed and utilized with a great success is cryptography. Cryptography comes into play when we need to hide some data from somebody. And one of the most common scenarios is sending a private message over an insecure channel. The scenario description usually involves three entities, which can be person, computer programs, or whatever. These entities are usually named Alice, Bob, and Eve. Alice wants to send Bob a very private and sensitive message. And the only channel she can use for this task is eavesdropped by Eve. No way Alice can afford Eve to know the content of this message. Thus, she needs to encrypt it. There are plenty of ways to encrypt the data, including highly effective ones, which guarantee the message safety. But the problem here is in the following contradiction. Protecting the message from Eve is not enough. Alice must provide the possibility for Bob to read the encrypted message. So we must protect the data from one participant and make it available to another participant. And if these two participants, Bob and Eve, are completely indistinguishable for Alice, if they initially share the same amount of knowledge and other attributes, then the problem becomes insoluble. So we must presume that Bob is somehow different from Eve. For example, some time ago, Bob had a private conversation with Alice, and they managed to generate a shared secret key. If the length of the key is not less than the length of the message, and if this key was successfully kept away from Eve, then Alice can securely encrypt the message, and only Bob would be able to read it. The encryption algorithm in this case may be as simple as bitwise XOR of the message and the key. For Eve, the result of this XOR would be incomprehensible gobbledygook. But Bob has the same key as Alice, and the repeated XOR with the encrypted message will reveal the original message to him. Having the opportunity to share a secret key is a very good option, but it often can't be afforded. First of all, to be completely secure, Alice and Bob would need a new shared key for each new message. Or they would need to generate a very long key sequence, which will cover their private conversations long enough before the next opportunity to generate the shared key. This solution is not bad, and I believe it is still used quite often. But the problem of keeping these long sequences in secret is still one of the weakest points of this approach. And of course, there are situations where Alice and Bob never had an opportunity of a private conversation. This is actually the most frequent case. The video that you are watching right now was received by your browser from the Coursera server over the secured channel. But your browser and Coursera server never met in private. And to get this video from the server, your browser uses the network which is presumably teeming with eavesdroppers. How did your browser and the Coursera server manage to create the shared secret key? The most probable answer is they managed to do it thanks to the SSL cryptographic protocol, which itself is based on asymmetric cryptography algorithms, such as RSA. And the RSA algorithm is based on computational asymmetry of multiplication and factoring. However, for quantum computing, thanks to Peter Shor's result in 1994, both these tasks, multiplication and factoring, are rather easy, which makes the RSA algorithm vulnerable for large enough quantum computer. But in 1984, 10 years before RSA became unsafe, two American scientists, Charles Bonnet and Gilles Brassard, invented the cryptographic protocol which is absolutely safe for the shared key creation and distribution, thanks to null cloning theorem.